Let's now look at an example of finding the area between two different curves where one of them is a mathematical relation and we're looking at the region that's shaded where they're enclosed. So the area between these two curves, when I graph them, I get an enclosed region right in here. So we're talking about this area. Now for this particular example, I have the parabola x equals 3 minus y squared. So it's a parabola on its side. Now if you're not really comfortable graphing these to start with, you can, for that x equals 3 minus y squared, make an xy chart just to get some ordered pair of points to graph. Just plug in for your y instead of in for your x. So for example, if y is equal to 0, well, I have 3 minus 0 squared, or x is 3. If y is equal to 1, then I have 3 minus 1 squared. Well, 3 minus 1 is going to give me an x value of 2. If I have a y value of negative 1 quantity squared is 1 still. So 3 subtract 1 gives me an x value of 2. And you can do that for some of the other ordered pair values as well. And when you plot those points and draw the picture of the mathematical relation, remember this isn't a function but it's a mathematical relation, I get this parabola. Now the other graph is y equal x minus 1. So this is just a line with a y-intercept of 0, negative 1 and a slope of 1. So we graph our y-intercept of 0, negative 1, our slope of 1, and we get that as our line. So those are our graphs. When I look to see what the best way to do the integration would be, if I hold my subrectangles vertically so that it would be with the differential dx, as I scan from left to right across the interval, at first the pink curve, the pink line is on the top of the region and the black parabola is on the bottom. But when you get about right here and then keep going right, do you see how the bottom of the parabola and the top of the parabola, so the top of the parabola and the bottom of the parabola, I don't have consistency of which equation is always on the top of the region and which one is on the bottom. So we can kind of like think of another maybe orientation that we could take in order to find this area. Hold the subrectangles horizontally, scan from bottom to top, and we see as we go across the region, the black curve is consistently to the right of the region and the pink line is consistently on the left of the region, all the way as I go from bottom to top. So as you go from bottom to top, your black curve is on the right of the region and the pink curve is on the left of the region. So actually what I want to do here is run my subrectangles horizontally, which means I would be taking the differential dy. Now when we do the differential dy, we actually integrate it from the lower y value of the ordered pair to the upper y value of the ordered pair. And we're going to take our curves right minus left. And when I'm working with the differential dy, I have to have my equations x equal an expression in y's. So here, when we're looking at this, I have my integral. The right curve is my parabola, and x is on a side by itself is equal to an expression in y's. So that's my 3 minus y squared minus. Now this equation is not set up yet to have it in terms of the differential dy. I need to solve that for x in terms of y. So we'll add a 1 to both sides. X is equal to y plus 1. And so that is the curve that is on the left of the region. It has more than one term, so I have to put it in parentheses. Okay, now what about the y values? Well, as I look from bottom to top, it starts at a y value of -2 for the region, and it tops out at a y value of 1. If that wouldn't be easy to see in the way that we graphed it, then what we would want to do is to look at substitution. And since x is equal to 3 minus y squared, and y is equal to x minus 1, and I want to find the ordered pairs that make them both true, I can plug in the 3 minus y squared in for the x, make it an equation all in y's, and then solve for the y's that make that true. Okay, so let's get back to our integration. When we look at from -2 to 1 of 3 minus y squared, and then minus y minus 1 dy, we're going to combine like terms. So 3 subtract 1 is 2 minus y squared minus y dy. We can now find this definite integral by doing the antiderivative of the integrand and then plugging in the top number minus plugging in the bottom. So this is the integral of 2 dy is 2y. The integral of y squared is 1/3 y cubed. The integral of y to the first is 1/2 y squared. And we're going to evaluate that from -2 to 1. So plug in the top number, plug in the 1. Minus, plug in the -2. And when you work that all out, you'll get an area of 9/2. Or you can write that as 4.5.